Hello, everyone. I am very happy to learn the radian with you today. In the previous lecture, we have learned the concept of arbitrary angle. Today, we will further explore the measurement of arbitrary angle. First of all, let's review what units of angle measurement we learned in junior high school. Good. Degrees, minutes, and seconds. So how is the angle of 1 degree defined? How to convert degrees, minutes, and seconds? We divide the circumference of a circle into 360 equal parts, and the center angle corresponding to each equal part of the arc is called the angle of 1 degree. This system of units for measuring angles is called the angle system, and 60 base conversion is used between degrees, minutes, and seconds. Do you know what 60 degrees plus sine 60 degrees is? Some students will say that the two quantities cannot be added together because the units are different. 60 degrees is an angle, and 60 base is used. Sine 60 degrees is a real number, using 10 base. In life, different units should be used to measure different quantities. Even the same quantity can be measured in different units. For example, the height can be measured in meters or rulers, and the weight can be measured in tons and kilograms or grams according to different conditions. Is the measurement of angle only known from the angle? Mathematicians have faced the same confusion in history. In the 6th century AD, Indian mathematician Iapoto found a problem hard to explain when he was innovating to make a sine meter. For example, sine 30 degrees is equal to 0.5. Do you know what problem he found? In this equation, there are two different systems of units. The left side of the equation involves the channel corner, which uses the 60 base system. The right side of the equation is a real number which uses the 10 base system. Two mathematical objects of different units are distributed on both sides of this formula, so Iapoto wondered whether the diagonal measurement could use the decimal system. We should study this problem. First of all, according to the definition of any angle, rotate the endpoint O of the ray OA around to OB to form the angle alpha. In the process of rotation, there is a point P and P on the ray OA, which is different from the endpoint O. Its trajectory forms an arc, that is, alpha equals n degrees. In order to unify the unit system of angle into base 10, we must use the quantity represented by decimal system. Two quantities are involved in this process, namely arc length and radius. To study this problem, we might as well take more points. I take 3 points on ray OA, A1, A2, rotate to points B, B1 and B2 respectively. What quantities are involved in this process? Can you find the equal and unequal relationship between them? Through analysis, we find that there are 3 quantities here: arc length, radius, and center angle. The arc length and radius are changing with this motion, while the center angle is unchanged. This is bound to lead to a question: what is the relationship between the arc length, radius, and center angle? Can we use the mathematical formula we have learned before to express the relationship between them? Some students will say that we learned the arc length formula in junior high school. This formula shows the relationship between the arc length, radius, and the center angle. Can you explain it by using the arc length formula L equal to n pi r of 180? In this process, the arc length and radius have changed, while the center angle remains the same. Because the center angle is related to the arc length and radius, according to the arc length formula, we can get that the center angle n is equal to 180 parts of pi multiplied by L ratio r. When L ratio r is a fixed value, the center angle n remains unchanged. When the center angle of the circle is constant, the L ratio r is equal to n of 180, and pi is a fixed value. We find that the ratio L over r of arc length and radius is only related to the size of the center angle. When the center angle is determined, L over r is also uniquely determined, and when L over r is determined, the center angle is also uniquely determined. This makes us think that we can use the real number L to r to measure the size of the angle. When the arc length and radius are equal, the ratio of L to r is a fixed value of 1. At this time, the center angle is equal to 180 degrees of pi. We record the ratio of L to r as an angle of 1 unit. In this way, the size of the angle can be measured by the ratio of L to r. For example, when L ratio r equals 2, that is, when L is equal to 2 revolutions, the center angle of the circle is the angle of 2 units. When L ratio r is equal to 0.5, that is to say, when L is equal to 0.5 revolution, the center angle of the circle is 0.5 units. In this way, L ratio r can be used to measure the size of the angle. Here L ratio r is a real number, which solves the problem of measuring the size of the angle with a real number. This leads to another system of units and radians for measuring angles. The units of the radian is represented by the symbol rad and read as radians. The central angle of an arc with a length equal to the radius is called an angle of 1 radian, which is recorded as 1 radian, as shown in the figure. Can you make an angle of 2 radians according to the previous analysis? According to the concept of radian system, alpha is equal to L, then R is equal to 2, that is, L is equal to 2 revolutions. The central angle of the arc length is 2 radians. In the same way, can we make other sizes of angles? Sure, for example, an angle of 3 radians. Can any corner of it be represented by a real number L over R? How to specify the number of positive angles, negative angles, and radians of leaders. In the previous exploration, we know that when the radius is fixed, the rotation of any angle can be measured by the arc length. Its symbol can be determined by the direction of rotation. Therefore, any angle can be represented by a real number L over R. The radians of positive angle, negative angle, and adjacent angle are expressed by positive number, negative number, and 0 respectively. So we made such a provision. If the arc length of the center angle alpha of a circle with radius r is L, the absolute value of the radian of the angle alpha is the absolute value of alpha equal to L then r. Here, the positive and negative of alpha is determined by the rotation direction of the terminal edge of the angle alpha. Conversely, can any real number represent an angle? Is this expression unique? For any real number, if the ratio of L to R is equal to the absolute value of alpha, then L is equal to the absolute value of alpha multiplied by R. At this time, the absolute value of alpha is determined, and then the positive and negative of alpha is determined by the rotation direction of alpha. So any real number can represent a unique and definite angle. Therefore, any real number can represent a uniquely determined angle, and any angle can be represented by a uniquely determined real number. Then we establish a one-to-one correspondence between the set of angles and the set of real numbers. The exploration of human diagonal has experienced a long historical process. The radian system was proposed by the Swiss mathematician Euler in the 18th century. In his famous infinitesimal analysis theory, he first advocated the use of radian system to unify the units of angle and length, which greatly simplified the study of trigonometric functions. The word radian was born in 1873. Professor James Thomson, an Irish engineer, creatively first used the word radian in an examination question compiled by him. It combines the first 4 letters of the radius with the first 2 letters of the angle to form a new word radian. It is widely accepted and still used today. So now we have 2 units of measurement for the diagonal, the angle system and the radian system. Then our problem is, how are they converted? We rotate the end of the angle by 1 turn. The radian number of the obtained perimeter angle is 2 pi, and the angle is 360 degrees. That is, 360 degrees is equal to 2 pi radians. After simplification, we get that 180 degrees is equal to pi radians. We can get it by deforming this formula. 1 degree is equal to pi radians of 180 parts, which is approximately equal to 0.0175 radians. The same radian is equal to 180 degrees of pi, which is about 57.3 degrees. Equal to 57 degrees and 18 minutes, we can convert between angle system and radian system on this basis. Now let's look at such an example. Example 1. Divide 6730 into radians, and change 3.14 rad into angles in question 2. Requirements expressed in degrees, accurate to 0.001. Because we know that 1 degree is a radian equal to 180 parts of pi, we first divide 67 degrees 30 into 2 parts of 135 degrees, so 67 degrees 30 minutes is equal to 2 parts of 135 times 180 parts of pi. After simplification, it is equal to 3/8 pi radian. In the study of trigonometric functions, we often involve the exchange of radians and degrees of special angles. Now please try to fill in the following table of degrees and radians of special angles. First, let's see that the number of radians corresponding to 0 degrees is 0 radians. Because 30 degrees account for 1/6 of 180 degrees, 30 degrees is equal to the radian of 6 pi. Similarly, 45 degrees is equal to a chord of 180 degrees. So 45 degrees is equal to 1/4 of pi in radians. So how can the third pi radian be converted into an angle? In the previous analysis, we found that the pi radian is 180 degrees, so the direct substitution of 180 divided by 3 degrees here is equal to 60 degrees. Or as we understand it this way, the third pi is equal to twice the sixth pi, so the third pi is 2 times of 30 degrees and converted to 60 degrees. Similarly, 2pi equals 180 degrees. Converted to an angle equals 90 degrees. We can also understand that 1/4 of pi corresponds to 45 degrees. Half pi is twice as much as 1/4 pi, so half pi corresponds to twice as much as 45 degrees and 90 degrees. So how to convert 120 degrees? We can see that in terms of quantity, 120 degrees is twice as much as 60 degrees, so it is converted into arc degrees equal to 2/3 of pi. Similarly, 135 degrees is 3 times that of 45 degrees, so it is converted into 3/4 of pi radians. 150 degrees is 5 times that of 30 degrees, so it is converted into an arc of 5/6 of pi. Pi is clearly equal to 180 degrees, 3/3 of the radian of pi, where pi is directly converted to 180 degrees. So it is equal to 270 degrees, which can also be understood as that 3/3 of pi is equal to 3 times of 2/3 of pi, so it turns out that 3 times of 90 degrees is equal to 270 degrees. Similarly, 360 degrees is equal to 2 pi radians. In our previous study, you are very familiar with the calculation of angles. But in the future study, we should learn to use radians to express the special angles we are familiar with. In the same way, let's look at the second question. Because we know that 1 radian equals 180 degrees of pi, the radian of 3.14 equals 3.14 times 180 degrees of pi, approximately equal to 179.909 degrees. Here we need to pay attention to that when the size of an angle is expressed in radians. Radians can be omitted as long as they do not cause misunderstanding, but the unit of radians cannot be omitted. Example 2. Use an the radian system to prove the following formula about the sector. First, L equals alpha r. The second S is equal to the square of 1/2 alpha r. Third, S is equal to 1/2 of LR, where r is the radius of the circle and alpha is the center angle of the circle, and its range is specified to be greater than 0 and less than 2 pi. L is the arc length S sector area of the sector. Now let's see the proof of this formula. From the radian value formula, the absolute value of alpha is equal to L over R, where alpha is a quantity with practical significance, so alpha is greater than 0. Therefore, we can directly remove the absolute value sign and get that L is equal to alpha R, thus proving that we only need to prove 2 and 3. In junior high school, we learned that the arc length formula and area formula of a sector with radius r and center angle n degrees under the angle are L equal to n pi r of 180 S is equal to the square of 360 parts n pi r. Convert the center angle of the circle into radians to obtain alpha equal to n pi of 180. By substituting it into the formula, it is obtained that S is equal to 360 n, and the pi r square is simplified to obtain that S is equal to half the square of alpha r. Then substitute L equals alpha r into the above equation. You can get that S is equal to 1/2 LR. Through this question, you can find that the radian formula can greatly simplify the area formula and arc length formula of the sector. In the future study, we will further realize that the introduction of radian formula brings more convenience to our calculation. Okay, through today's study, let's make a summary. Today we learned a new measurement system for arbitrary angles, the radian system. The essence of radian system is to use the length of line segment to measure the size of angle. If the arc length of the center angle alpha of a circle with radius r is L, the absolute value of the radians of the angle alpha is the absolute value of alpha equal to L then r. The positive and negative of alpha is determined by the rotation direction of the middle edge of the angle alpha. Second, radian units are represented by the symbol rad. Third, the radian value and angle value of any angle can be converted. We specify that 1 radian is equal to 180 degrees of pi, and 1 degree is equal to 180 radians of pi. Okay, that's all for today's study. Goodbye.